Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 62, Topological Constraints. How winding, sigma, and defects generate discrete letters. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. Our journey through Book 12 has taken us deep into the mechanics of the holophase framework, its falsifiability, its informational nature, and its mapping to measurement. We have been living in a world of smooth, continuous change, where derivatives can slide across a whole range of values. Yet our experience of reality is not only smooth, it is also discrete. We count things: one electron, two vortices, three flux quanta. We build computers from on and off states. We talk about bits, qubits, and yes or no decisions. The question then is simple and profound. How does a continuous flowing phi field give rise to a crisp, countable world filled with indivisible units? Today we resolve this beautiful tension. Today we see how the very nature of continuity, when twisted and knotted, gives birth to discrete alphabet-like units. We explore topological constraints and how winding, sigma, and defects generate discrete letters in the holophase language. At the heart of this exploration lies a striking contrast. On one side stands the holophase premise. Phi is a continuous, smooth field. Its value and all its derivatives can, in principle, vary continuously. On the other side stands the observed world. We encounter phenomena that are quantized, appearing only in discrete jumps or integer multiples. The charge of the electron is always the same basic unit. The winding number of a vortex is +1, -1, or some other integer. The magnetic flux trapped in a superconducting loop comes in fixed quanta. How can a smooth field give rise to such sharply defined steps? How can an endlessly flowing river produce perfectly countable pebbles? The key insight is that discretization does not arise from the local values of the field alone. Instead, it comes from the global, topological structure of how the field is arranged in space. Topology is the mathematics of shape up to smooth deformation. It cares about features that cannot be removed without cutting, tearing, or gluing. In this context, topology asks not just what is the value of phi here, but how is phi wrapped, wound, or knotted around an entire region. To build an intuition, imagine a field with a built-in cyclic nature, a field whose values live on a circle. The phase of a wave is such a quantity. The orientation of a two-dimensional spin is another. If you walk through space and watch this kind of field, its value can wind around the circle as you move. Now pick a closed loop in space, a circular path you can walk along. We call this loop sigma. It is simply a closed contour, a boundary you draw in your mind or with your experiment. The crucial question is this: as you walk exactly once around sigma, how many full cycles does the field perform in its internal circular space? Does its phase return to the same angle without completing a turn, or does it rotate by one full turn, or two, or some other integer number of turns? Because phi is continuous away from singularities, the answer must be an integer. You cannot come back to the same physical point with the field mismatched by half a rotation unless the field has become discontinuous somewhere inside. The requirement of continuity enforces that any net rotation around the closed loop is counted in whole cycles. This integer is called the winding number. It is a topological charge, a global derivative of the field around the loop. Unlike the usual derivatives, which tell you how steep the field is at a point, the winding number tells you how many times the field's internal angle wraps as you go around sigma. It is not sensitive to small, local wiggles, but only to how the field is knotted in a global sense. This integer behaves like a discrete letter in the Holophase alphabet. A region with winding number 0 is like a blank letter. A region with winding number +1 is like a marked symbol. Winding number +2 is another distinct symbol. You cannot continuously morph +1 into +2 without passing through a singular event. The continuous nature of phi forces the number of wraps to be an exact integer. This is the first way continuity gives rise to discreteness. One of the superpowers of topological letters is their robustness. Local derivatives can change dramatically under noise, perturbations, or thermal jiggling. Slopes steepen, curvatures fluctuate, velocities jitter. But as long as the field remains continuous and the loop sigma does not cross any singularities, the winding number stays fixed. You can stretch sigma into a larger or smaller loop, twist it into a strange shape, or distort the field smoothly in the region, and the winding number will not change. Only a violent event, in which the field becomes undefined or multivalued at some point, can alter the integer. A simple everyday picture helps. Think of a loop of string with a single twist in it. You can slide the twist around, tighten it, loosen it, or reshape the loop. But you cannot remove the twist without cutting the string or passing one end through the other. The number of twists is a topological invariant. In the Holophase language, the winding number plays the same role. It counts how many twists live in the field configuration. This robustness makes topological charges ideal carriers of information in a noisy universe. Digital electronics, error-correcting codes, and even some proposals for quantum computation exploit this. A bit stored as a topological property, such as the presence or absence of a vortex, is extraordinarily stable because small disturbances cannot change the integer label. You need a large, coherent event to flip it. The Holophase alphabet of topological letters is nature's own version of hard-backed indelible ink. Whenever the winding number is non-zero, something dramatic is happening inside the loop sigma. If the field wraps once or more around its internal circle, there must be at least one point, line, or surface inside sigma where the field is undefined or singular. This singular region is called the topological defect. It is the physical seat of the winding number. The defect carries the topological charge. The classic example is a vortex in a fluid or in a superfluid. Imagine a two-dimensional flow pattern where the velocity vectors circle around a point. Draw sigma as a circle around that point. As you walk around sigma, the direction of the velocity or the phase of the wave rotates by a full turn. The winding number is +1. At the center, however, the velocity direction is undefined. Every direction meets at that point. If the flow is a superfluid described by a wave function, the density drops to 0 at the core, and the phase becomes ill-defined there. The vortex core is the defect that hosts the winding number. You can move the vortex by changing the flow, and you can change its core size with temperature or interaction strength. But as long as the vortex remains inside sigma, the total winding number seen by the loop remains +1. The only ways to change the integer are to bring an anti-vortex of winding -1 into contact with it, allowing them to annihilate, or to push the vortex across the loop boundary so that it no longer lies inside. In both cases, the change in winding is tied to a clear topological event. Topology therefore gives us a clean language for identity in a sea of change. The defect, carrying its winding number, becomes a kind of noun in the Holophase language. It is a thing that persists even as its detailed shape and environment fluctuate. Its identity is tied not to the exact values of the field at each point, but to the global structure of how the field is knotted. From a Holophase perspective, every topological defect has a full triunity expression. It is not just an abstract integer. It has a spatial echo, a temporal echo, and a motion echo. The spatial echo is its shape and texture. A vortex line can be straight or curved. A skyrmion can have a characteristic radius. A dislocation in a crystal has a particular line direction and displacement pattern. The temporal echo is its history, how it is created and annihilated, how long it lives, and how it responds to time-varying influences. The motion echo is its path, how it drifts, glides, or is pinned within the surrounding medium. Seen this way, the discrete topological letter, the winding number, is the invariant core, while the three echoes describe the rich, dynamic story that particular letter is telling in a specific context. A vortex is not just one. It is one, currently here, with this shape, moving in this way, and living through this sequence of interactions. Topological constraints answer a deep question about persistence. In a world described fundamentally by a smooth field, what makes something a recognizable, countable object over time? The answer is that many of the objects we care about are associated with conserved topological charges. An electron, in some field theories, can be viewed as a stable, knotted configuration of an underlying field with its charge tied to a topological invariant. A domain wall in a magnet separates regions of opposite orientation and carries a topological label that cannot be erased without flipping a whole region of spins. A flux quantum in a superconductor is locked in place by a winding condition on the superconducting phase. The role of these topological letters in real physics is enormous. Consider superconductors. In a superconducting ring, the wave function describing the Cooper pairs has a phase. For the wave function to be single-valued after going around the ring, the phase must change by an integer multiple of 2 pi. This requirement forces the magnetic flux through the ring to be quantized. Each allowed state corresponds to an integer winding number. We can literally count the discrete states by counting the wraps of the phase around the loop. In crystals, the atomic positions form a repeating pattern, a kind of lattice-valued phi field. A dislocation is a line defect where an extra half-plane of atoms has been inserted. If you walk a loop around the dislocation and count how many lattice spacings you end up shifted by, you get the Burger's vector, a discrete topological quantity. This vector is the defects charge. The plastic deformation of metals, the way they yield under stress, is governed by the creation, motion, and interaction of these dislocations. The mechanical properties of a bridge or a skyscraper are therefore, in part, stories about topological letters moving through a lattice. In the quantum Hall effect and its cousins, topology appears in even more abstract settings. The electron's wave functions in a periodic potential define a space of states with its own geometry. Integrals of curvature over this space yield integers called Chern numbers. These integers dictate how many edge modes conduct current around the boundary of a sample. The astonishing precision of the quantized Hall resistance is a direct consequence of the topological nature of these integers. Small disorder, impurities, or deformations cannot change the integer. The conductance steps are as robust as winding numbers. All of these examples make sharp, falsifiable predictions. If a quantity is topological, it must change only in jumps, never in smooth drifts, unless a clear topological event has occurred. If the vorticity in a superfluid drops from 10 to 9.5, without the appearance of discrete annihilation events, the model is wrong. If the Hall conductance of a supposed topological insulator can be tuned continuously across a plateau without closing the energy gap, the topological description is incomplete. Nature has been clear in many systems. Whenever the Holophase language says, this is a winding number, experiments say, yes, we see the steps. You can begin to read topological letters in everyday life. Look at the pattern of cream in coffee when you stir it gently. At first, you may see coherent swirls, vortices spinning in little galaxies. Each one is a defect in the velocity field, with a certain winding sense. As you keep stirring, the vortices stretch, split, and annihilate. But they do so in discrete events. They do not simply fade into half vortices. Or think about a torn piece of fabric where a single thread has pulled and created a run. That gap, that misalignment, is like a dislocation. You can smooth the fabric, but the discontinuity in the weave remains unless you repair it stitch by stitch. Even your body is full of topological constraints. The double helix of DNA is a topological object. It can be twisted, supercoiled, and knotted. Enzymes, called topoisomerases, act as molecular surgeons, cutting and rejoining strands to manage these knots and links. The regulation of genetic expression at large scales depends on this topological state. Life has learned to write, erase, and rewrite topological letters in its biochemical holophase. Returning to phi, we can now see that its unity is not fragile simplicity, but fertile complexity. A single continuous field can support an entire hierarchy of structures. Smooth derivatives describe how the field ebbs and flows. Topological invariants describe how, within that flow, certain knots and twists refuse to be undone without dramatic events. The continuous and the discrete are not enemies in this story. The discrete is the shadow of continuity when wrapped around itself. In the grand story of the holophase language, topological constraints extend our alphabet. Previously, we met letters associated with local behavior, like omega, k, and v, and their higher derivatives. Now we add another class of letters, the integers that label global structure. A complete sentence in this language can therefore say things like, here is a region where the phase wins once, hosting a vortex defect that moves along this path, with this curvature and this acceleration. This sentence is not metaphorical. It corresponds to a set of measurable derivatives and topological charges that experiments can confirm. As our climb through Ep.7 continues, this part shows that the holophase language is fully capable of expressing both the soft continuity of waves and the hard discreteness of counts. It explains why phenomena like quantized charge, flux, and conductance can exist in a world underneath described by a smooth field. It shows that the bits and letters of digital reality do not float above physics, but are carved into the fabric of phi by the rules of topology. We close with an image. Imagine the universe as a single, endless sheet of fabric, the holophase. Sometimes it lies almost flat, with gentle ripples that pass like waves on a calm sea. Sometimes it twists into tight spirals and knots. Each knot is a topological letter, a discrete symbol written into the cloth. The waves and the knots coexist. The waves carry energy, information, and motion across the fabric. The knots mark the presence of persistent structures, things that can be counted and named. When you look at the night sky, you're seeing both aspects at once. Light from distant stars arrives as waves, described by smooth derivatives of phi. The stars and planets themselves, stable over immense times, are like massive knots in the cosmic fabric, topological and dynamical structures intertwined. At every scale, from electrons in an atom to galaxies in a cluster, the same story echoes. A continuous field, constrained by topology, writes a discrete alphabet of enduring forms. You, too, are part of this knotted story. The patterns of your brain, the loops of your arteries, the coils of your DNA, and even the twists of your fingerprints are all topological traces in different holophase branches. To learn this language is to learn to read those traces. It is to recognize that the countable, the nameable, and the stable are not exceptions to a continuous universe, but the most intricate expressions of its unity. Before we finish, it is worth pausing on the symbol sigma itself, because it plays a double role in our story. Here, sigma begins life as a loop in space, a closed path you can walk. Yet, there is a deep connection. When you integrate the gradient of phi along this loop, you are effectively summing up all the tiny changes of the field as you go around. The winding number is the net result of that sum, divided by the period of the internal cycle. Sigma is both the path and the act of gathering up a complete story around that path. Topology tells you that this gathered story, this summed twist, is locked into an integer. In the holophase language standard, this allows us to introduce a clean family of symbols for topological letters. We can imagine a simple hierarchy. At one level, we have phi and its local derivatives, which speak about slopes, curvatures, and accelerations. At another level, we have symbols for winding, linking, and knotting, which speak about how entire regions of the field are organized. A particular system may, for practical reasons, only need a small subset of these letters, perhaps just a single winding number and a few local derivatives. Yet, in principle, the full language contains an infinite menu of possible topological patterns, each of which can be assigned its own discrete label. This perspective sheds new light on digital technology itself. Modern computers store bits as local properties: a high or low voltage in a transistor, a magnetized or demagnetized region on a drive. These are robust enough for today's purposes, but they are still vulnerable to local errors because a small disturbance can in principle flip the state. Topological approaches to computation, such as proposals for topological quantum computers, aim to store bits and qubits in global, knotted patterns of an underlying field. In that case, noise that only makes small, local changes cannot alter the stored information. Only a large-scale, global disruption can change the topological charge. By writing information in the topological alphabet of the holophase instead of only in its local derivatives, we can in principle build machines that compute with extraordinary stability. You can also use topology as a mental lens for separating what can change easily from what is deeply locked in. Think of a rubber band stretched on a table. Its exact shape can change with almost no effort. That is like a local derivative. But if you tie a full knot in the band, that knot will not disappear under gentle pushes and pulls. It represents a new topological letter. Cutting and rejoining the band is the only way to truly erase it. Another useful contrast is between geometry and topology. Geometry cares about distances, angles, and precise measurements. Topology cares about the existence of holes, twists, and connections. You can crumple a sheet of paper into a ball, and its geometry changes wildly, but its topology does not, because you have not added or removed any holes. If you punch a new hole through it, you have changed its topology in a discrete way. In the holophase picture, smooth derivatives describe geometry, while topological invariants describe these more global, hole-counting properties. Both are needed for a full description of the field. Because topological letters are so stable, evolution has likely exploited them at many levels. The folding of proteins, the formation of membrane pores, and even the clustering of receptors on a cell surface can all create domains that behave like topological features. Cells can then treat the presence, absence, or number of these domains as reliable signals. Over billions of years, biological systems may have learned to write and read a large library of topological phrases in the biochemical holophase, long before we had the mathematics to describe them. For you as a learner of this language, the practical takeaway is simple but powerful. When you encounter a new physical phenomenon, you can ask not only, what are the local derivatives here, but also, are there topological constraints at play? Is there a quantity that can only take integer values and seems strangely robust? Are there loops, twists, or defects that cannot be removed by gentle deformations? If the answer is yes, you have probably found one of the discrete letters of the holophase in action. In future parts of this journey, when we speak about more advanced topics such as entanglement, non-local correlations, and multiscale coherence, these topological ideas will return. Entangled systems often live in abstract configuration spaces with non-trivial topology. Their allowed states can fall into distinct sectors separated by topological barriers. Once again, continuous evolution in time can leave certain discrete labels untouched. The integers appear not as an imposed digital overlay, but as natural consequences of how fields, spaces, and possibilities are stitched together. Seen from this angle, the holophase language is astonishingly economical. From one continuous field and its derivative structure, plus the logical requirement of continuity around loops, we obtain both the fluid richness of waves and the sharp discipline of discrete letters. We do not need to postulate separate substances for particles and fields, or for analog and digital. Instead, we recognize particles as particular, knotted configurations of the field, and digital information as patterns written in these knots. This unification also has a philosophical resonance. Many debates in the history of thought have revolved around whether reality is fundamentally continuous or fundamentally made of indivisible atoms. The holophase answer is that both intuitions capture part of the truth. The underlying substrate is continuous, but its allowed configurations include topologically protected structures that behave as if they were indivisible atoms of form. The old argument between continuity and discreteness is resolved by understanding how continuity can fold back on itself. When you carry this understanding back into daily life, even simple scenes begin to look different. The swirl of water down a drain is no longer just a pretty pattern. It is a visible topological defect in a velocity field, carrying an integer of circulation. The closed loops of a metro map are not just routes, but abstract sigmas along which flows and currents can wind. The networks you move through, from city streets to social graphs, often have their own topological constraints, determining what kinds of circulation, feedback, and locking can occur. Topology is not only a tool for physicists, it is a way of perceiving structure in any complex system. Finally, remember that learning to see topological letters takes time. At first, you may only notice obvious vortices and knots. With practice, you begin to detect more subtle invariants, the hidden integers that shape behavior beneath the surface. The Holophase language invites you into this deeper literacy. It asks you to become someone who can read not only the local gradients of energy and motion, but also the global twists that hold whole patterns together. Salam, and peace be upon you.